All right, welcome back. Let's see, there's a question about grading of project 1, so let me repeat that for the DB audience. Let's see, if we found that your code failed, but you think your code worked, there were some things, for example, the / comment is not ANSI C, so the Linux compiler doesn't recognize it. Microsoft is non-standard. They recognize it. They do lots of other non-standard things. So the TA knew that. So he edited your code to put in standard comments if necessary. If there are other problems, for instance, if there's a minor flaw, maybe you found your code mostly worked but failed on one example. It could be that our test just hit that trigger point. So I'm more than happy to work with you to figure out what exactly happened between Windows and Linux and that sort of thing. That's why I mentioned earlier that tell us if your code works or not. And if you tell us it works and then oops, we found it didn't, well then, clearly we got to maybe try it on Windows. Maybe you did test it on Windows and we tested it on Linux. Maybe there could be a different memory fault there. There's probably if this happens, there is a flaw in your code, but it's more minor than what it appears if it works on Windows but not Linux. So, or if it works in your test but not our test. I mean, we test it with a pile of matrices, and you tested it with some matrices, presumably, and so those test sets could differ. I think, I was assuming for project 1 you do your own testing, maybe to simplify this, so we can agree on a collection of matrices. I'll write up a short test script for project 2 that we'll use, and so you can test against those, so we can at least be testing on the same matrices. I mean, if the code works, it'll work on any set of matrices, so I didn't really think to narrow that down. But do test it on a lot of matrices. That's why I have a collection of 2,500 of them. Okay. For my own benefit. Obviously, you're not going to test on that many yourself, but so I'm more than happy to, like I said, to do regrades based on, those kinds of issues. So for project 2, are there any questions about project 2? I did have one question over email, I think. Was it yours, wasn't it, Debbie? About can I use the Gatsby operation? Y equals AX plus Y. And the answer is no. No Gatsby. You have to follow the pseudocode that I give you there. If you don't follow that pseudocode, you're writing a different algorithm. And the whole point of the project is to explore a different algorithm for doing the matrix multiplication. Your algorithm must be based on pairwise dot products of two sparse column vectors. Okay, so yeah.
Can you say do not do problem 2.18, but don't you have to do half of it to do the?
To do which?
You said for the dot product, it says look at problem 2.18, but don't do problem 2.18. Did you just mean don't do that problem?
No, you're doing. Well, okay, I said don't do problem 2.18 because in 2.18 you're considering two cases.
Okay, so you are doing B.
You are doing, in 2.18 it says consider two cases, the row indices of X and Y are not sorted, and then the row indices are sorted. Well, you can assume they are sorted. So you're doing, if you will, you're doing 2.18 2, but you're doing this, but then you're doing more than this because you're doing two matrices. You're not just doing two vectors. So that's why I referred to 2.18 in the project description, but the description itself is self-contained.
Okay. So don't you assume that for the problem that you're giving us, you're assuming that the matrices we're passing are n by n by 1 and 1 by n?
No, I'm going to give you m and n small, but not 1.
No. That you pass into the dot one?
I'm going to give you two. You're going to expect it to see two. You're going to do A transpose B. You're going to pass in A and B. You're not going to do a transpose.
Yeah.
I forget, in project 2 description, did I give you a name to call this function? I'm sorry?
CS underscore project 2.
Okay, CS underscore project 2. So you have CS underscore project 2. And this is just to help us simplify the grading. We can write one script. Okay. You pass in A and B. There's no transpose computed, right? I did make that clear. And so A and B are going to be matrices of this dimension, where the number of rows in each of A and B is k, and that could be large. So k can be very large, and your code should handle that just fine. M and n will be small. We could test it, certainly we will test it with m equals n equals 1. We'll do this, obviously, and so should you. In fact, that's the place to start. But we'll also test it with m and n small. In fact, we'll do mn much less than k. The product of m and n will be much less than k. The product mn will be small as well. So m times n will be small. By small, maybe 10 or 100 or something.
But for the dot product method, it's like a sub.
Right. The dot product.
You have to pass like something by 1. I mean, how do you?
Yeah, the dot product operates on column vectors. Yeah.
You're parsing it as a sparse matrix. You're treating it as a vector.
Well, no, you're not treating it as a vector. You're calling it many times.
As a 1 by n matrix.
No, you're not. No. You're not treating this as a 1 by anything.
Well,
what you're doing is you're pulling out pair by pair. You're doing all combinations of m and n to do the dot product, because you're doing Cij equals the dot product of the ith column of A and the jth column of B. So you will have a sub-method or a sub-program, whatever, that does this, that takes two sparse column vectors.
Okay, so
yeah, is that what you're asking?
Even though you're passing the matrix, we're kind of treating it as a vector.
Well, you're not treating A and B as a vector. That's where I don't want you to get confused.
Just for the dot product.
Well, of course, yeah. This is the matrix, and you pass in column by column. Right. Yeah. There's two different layers here, and the inside layer looks very much like problem 2.18, part 2. That's what this is, except in your case, you're doing two things. We're narrowing 2.18 because we're assuming that the columns are sorted with sorted row indices, but you're doing more because you're doing it on a matrix. Now, I had, one student in my office last Friday, and I gave some suggestions. I thought I'd duplicate them here. Let's see, if I remember, what order of things did I tell you to do? I'm trying to think. Let's see. Probably the first thing to do is just focus on the vector case. Because if you get this working, then it's easy. Then you can extend it later. If you want to do your project in installments, if you will, okay, and that can be helpful because then if you get a seg fault, at least you know that this part worked. If you get a seg fault here, okay, right, waterfall kind of thing. So you know where you're going. So write modular code, but you can start. Suppose you start with mn equals 1, and suppose you want to avoid seg faults. So you just pass in, two vectors. And you don't return anything. You just print the result on the screen. Okay? No worries about pointers and creating variables and messing up the MATLAB workspace. Just read it in, compute it, and print it out. Okay? Then worry about how to return it as a dense scalar, as a dense matrix scalar. Now, you're going to rip that code away because you're not going to return a dense matrix. You are going to return a sparse matrix. That's very important. I mean, I think I showed that in the project description, right? They made it clear the result should be sparse. C equals 8. You're computing this, and you're getting all three matrices are sparse. So we're working towards that. So this is a dense. So you work with this as a dense scalar. Okay. And if you get that back and get the right value and everything works, great. Okay. Now you extend it to return, and the f is, of course, your function, whatever it is. It's CS Project 2. It's just too long to write out. Then you extend it to get a dense matrix. Okay, now you're computing the whole matrix. You're doing the whole pseudocode. You're iterating through M and N. You're doing the dot product for every entry in C. But the advantage here is you can do this as a full matrix, and it's a little simpler because you have to do that anyway, right? You have to create a full matrix and then convert it to sparse. At least that's the suggestion I have. I mean, you technically don't have to even do that if you don't want to. Because you could go through C in column major order. You could just go down the columns one at a time, and you could actually write it immediately into a sparse matrix if you choose. You could do that. You could spallic a sparse matrix of the right size where the NZ max is M times N. You could do that. So you could combine the two steps if you wish. That's another alternative. You can do it either way you'd like. So, but the advantage of returning a dense matrix is now you can check your result in MATLAB. You can make sure that is C A transpose B. Oh, okay, it is. You know, did you get any seg faults? Oh, okay, you did or did not, whatever. And then once you get this working, then internally you convert C to sparse and return it as a sparse matrix, and that's the final step. But one advantage of doing this in this sort of incremental waterfall style is if you fail to finish the project. If you get stuck here, if you get this working but you get stuck on the sparse case, well, at least you get a good chunk of the project working, right? And then turn in what you have and then tell us, oh, by the way, this only works on scalars, you know. Okay, we can look at the code and see if you're on the right track. And then we can say, oh, by the way, tell us, please, don't let us figure out from your code what you did, okay? Tell us what you have and what you don't have. That's very important. Because if you don't have something and you turned it in and was like you didn't even realize you didn't have this part of the code, then it's like, what's going on here? You know, if you don't even if it's not clear from your project that you didn't even understand what you didn't do, that's a big problem, right? But if you understand that, okay, look, I got this working, but I had problems with the sparse case or whatever, tell us that, okay? Tell us what works and what doesn't. Anyway, so if you get partway through, like I said, then there's some substantial partial credit for just for getting this far. The other thing I mentioned too that's really important is as you're doing this dot product here, it's very important to exploit the fact that the columns are sorted, that the row indices are sorted, because then computing the dot product is akin. It's like the merge step of a merge sort, right? You've got two sorted lists of integer indices, and you're not producing a sorted result. You're doing the merge, if you will. You're not producing a list that's sorted that has everything, the set union. Okay, you're essentially finding the set intersection and then collapsing that down to a scalar by doing the multiply add, right? But in that process of doing that, you have these, if you will, two lists. Okay, and you look at the two lists and you look at the first two numbers in the list, and if they match, you do the multiply. And then you accumulate that in a scalar. And then you throw these two away. Don't throw them away, but you increment a pointer through these. And then you look at the next two integers. And if the row indices match, you multiply. If they don't match, you increment the one that doesn't match, and you, if you will, throw it away, because then that's multiplied by 0, so it doesn't add into your result. So it's a very simple loop. If you get too complicated, then something's wrong. The innermost loop, this is a very simple algorithm here. And it should be very fast on two large. You should get a speed of easily 1,000 over the MATLAB statement here for large enough matrices. Ed got a factor of 4,000, right? Huge. You should get a huge speed up over MATLAB, which is kind of fun to do, right? It's like, yes, I beat MATLAB, and they've been doing this for decades, right? So, is that clear now? Is that clear? Well, hopefully it was clear before, but maybe it's more clear.
Can we use CSN underscore drop 0 function when we convert from dense matrix to?
Let's see, convert from dense to sparse. Can you use the drop zeros? let's see. Yeah, that would be fine actually, because you're not destroying the algorithm. It's still asymptotically the same time in memory. So you're still illustrating the fact that yes, C is stored temporarily as a dense matrix anyway. Okay. If you do this, you do have a constant extra amount of memory because you've got all those extra row indices and column pointer. Well, just the extra row indices that you would never have had to have put in the data structure. So you have 50% more memory usage of your output than you may have had to have otherwise. If you tried to doing this extremely concisely. See, if I was doing this, well, I forget what I did. I have done this. The code, like I said, is actually inside MATLAB. It's just not used. This particular feature. I want to say that I actually compute in a dense matrix workspace and then copy it to sparse. But I think when I do that, I think, if I remember, I take the approach that this dense matrix is actually what I call my CX array. It's of size n squared, or m times n. And then I pack it in place to get the sparse matrix. That's what I do. So essentially I do a drop zeros in place, but I never create the row indices because, they're there. Why create the row indices of a dense matrix? You can compute them. You don't have to store them. So I compute them only at the very end. I think something like that. Anyway, because I'm worried. The part that I'm worried about in when I implemented this method. Of course, time is critical, but memory usage is critical. And you don't want to use this method if m times n is large. That's the limiting factor, is memory. Well, time as well. But if m times m is getting larger and larger, then this method becomes completely uncompetitive with the version that's essentially based on the sparse Gatsby, which is the one in the book. Okay, with the columns and the columns times sparse matrix times a sparse column, that method. And so since the killer for this method, the thing that will kill this method is the memory usage, I was trying to be very careful with the memory usage when I implemented it. Because that's what I'm bumping up against at the point at which, of course, if it gets so bad, then you wouldn't use this method at all. And my code selects automatically, looks at the two algorithms and decides, ooh, you're going to use way too much memory, and you're going to be, so use this one, use the other one instead. But if this thing uses small memory, then I'll use it. So I pick the one that uses least memory, is the approach I take. And then it's likely that the one I picked will also be the fastest one in practice, but it's no guarantee. So yes, you can use drop zeros because you're not changing the asymptotic, you're not destroying the asymptotic's memory or space of the algorithm. So you can do that, yes. And you're using the same algorithm. Not like using, for project 1, using CS compress, which is pointless because it's doing all the work. Anyway, for you already. So why do the quick sort? It's pointless. Okay, so is that all clear now? A good question, very good question. Good questions all. Fun stuff when you can actually, get a factor of 1,000 speed up over MATLAB. You feel really good when you do that. Yes. It's sometimes easy to do, sometimes really hard. I did a sparse QR factorization for the MathWorks, and I got one matrix. In one matrix, backslash would on one machine would take 11 days in MATLAB, the old MATLAB, but they're using a sparse QR factorization. And I got it down to 7 minutes. A factor of 2,000. Wow, that was fun. And I didn't make up a lot of those techniques, actually. I mean, that algorithm, the algorithm was already floating around out there. My implementation of it added some new theory, some new algorithmic points to it, but rather my contribution theoretically and algorithmically was actually rather modest. I just used essentially existing methods, but implemented them reasonably well, and then plugged them in to MATLAB. So, just that they had been using a very old algorithm, and a very simple one that works great on small matrices. But as the matrices get really, really big, and this one was a big one. This was millions by hundreds of thousands in size, for which MATLAB really wasn't designed for. That particular algorithm. But you can do it in MATLAB if you have the right algorithm. Okay, so asymptotics do matter. They do actually have a big impact. So, but it's fun, and it's fun too to see your work actually. People are using it, and not having to call you up. Oh, I got a seg fault. You can't. It's like, oh, it mostly works, and no, that's not good enough. It's got to always work. Because I can't afford to be called up every time somebody has a problem with backslash. Be ridiculous. All right. So let's go back now to the sparse triangular solve, and we'll probably have time to finish chapter 3 today. Next class we'll do chapter 4, which is this chapter 3 is a segue into the sparse triangular solve. Remember, is the major character in the novel here. Okay, so we're looking at. Okay, last class, just as a refresher, we looked at, let me go to the very end, here we go, the topological sort and the depth first search. Okay, we're doing this triangular solve, and if, say, B4 and B6 are non-zero, well, if B4 is non-zero, then that makes B9 non-zero because of that non-zero. And if X9. If X9 is non-zero, then that makes X12 and 13 non-zero. And this making of non-zeros is propagating through this collection of rules, if you will, which can be captured in this graph, and the graph is just the graph of the matrix. So 9 makes, if this is non-zero, then that makes 12 and 13 non-zero. So we need to do a graph traversal from nodes 4 and 6, and we need to find what's called a topological order, because where if two nodes are in the reach, and if there's a path from node A to B, then A has got to appear before B in the traversal, in the output. And that's called a topological order. It respects all the data, all the arrows. No arrows go backwards. And so the beauty of this is that that first search automatically produces a list in topological order. So now we've got to implement this algorithm to find the reach. And the reach will then be, since it's a depth first search and not a breadth first search, the reach of the result X will be computed in topological order, and it's being pushed onto a stack, and so it's stored in reverse order of the finish times for the depth first search. So the one that finishes first gets put at the bottom, at the very last. Okay, so now we looked at there's a recursive implementation of the algorithm, beautifully simple and beautifully mimics the pseudocode. All right, but this has a problem. Recursion causes typical machines to crash if the recursion depth is order n. So we got to do it by ourselves non-recursively. The top algorithm here, okay, is itself not recursive. So this thing is going to get mimicked on the next slide. So look at this picture, and it's actually also in the book if you have your book in front of you. It gets expanded into this with extra little twists here. So it still is a loop across the non-zeros in column K in the sparse B vector. one twist on this is I'm passing in a column index K of a sparse matrix B. So I'm expanding the algorithm to handle not just a sparse column vector, but a sparse column vector that comes out of a matrix. See, here I'm just assuming, oh, it's the first column in this matrix that I'm working on. But there's nothing. If I pass in a K here and put a K and a K plus 1, then I can pull out the kth column. And so now I'm doing a triangular solve using the right-hand side, which is the kth column of some matrix. And you'll see later why I want to do that. But it doesn't really change the algorithm. It just makes it a little more flexible. So that's one thing that's happening here. That's what the K is. Otherwise, it's identical. Okay. And this algorithm also assumes that the workspace, the stack, has been allocated xi, because this is script x, if you will, in the pseudocode. And it's got this funny p inverse as well. For the moment, ignore that. Literally, pretend this is a null pointer. It's not going to be, for now, it's not going to be used. I need it later in chapter 6. Okay, so you can forget this. This is just a little twist on the code, and I'm calling the matrix G, not L, and there's a reason for that because I want to this function actually was also going to operate on an upper triangular matrix just as easily as a lower triangular matrix. In other words, magically, this is going to do ux equals b as well as lx equals b transparently. Because the DFS will just go the other direction, not this direction. It's really beautiful the way that works out. So that's why I'm calling it a general matrix G and not L. Other than that, we've got the same algorithm. We have another change, though, is that I'm putting in a macro that asks me that I can ask, are you a marked node or not? Okay. And another macro that clears and sets the mark. So in here, I didn't worry about clearing the marks at the end. I used this W array to do the marking. And I don't bother about clearing it. So on output, W is going to be zeros and ones. Okay. But I don't want to do that in the more general purpose code because I have to worry about cleaning up after myself. But other than that, it's the same. There's the bottom of the stack. There's the stack initialization. The top pointer points. So there's a stack here, xi, of size n, and top points here. So I'm treating this vector x as a stack, and so this is holding my calligraphic x list of integers. And this is going to be pushing at the bottom right there. There's the push. Okay, so the marking, and I started talking about this last class, but it kind of went kind of quick. So the marking is rather peculiar. Like I said, there's lots of ways of marking and unmarking nodes in a cheap way. And the question is, do you want to save time or do you want to save memory? Do you want to save both? And in this case here, I wanted to save memory. I wanted to mark the nodes with no extra memory requirements at all. Now, I do have some workspace already. I've got x. Asymptotically, I could easily have another vector out here. It's not that big a deal. But I wanted to be parsimonious on memory usage. And so I wanted to mark the nodes using free memory, zero memory. How do you do that? The trick is to look at this is, if you will, LP or G. I'm calling it GP here. The column pointers of this matrix L that you're passing in are all greater than or equal to 0. So the sign bit on all those integers is 0. And I can just flip the sign bit. They're 2's complement numbers. So that sign bit, if it's a 32-bit integer, say, the very leftmost bit, it will always be 0 on input because it's a valid matrix. I've got no negative column pointers. That's ridiculous. But because if they started it at something, like if the first column pointer was not 0, I could negate that number, like if it was 1. I could negate it and get -1. And then I could take this. I could have the number line here 0. And if 0 is never used, if all I have are these numbers, 1, 2, and 3 and following, inside the vector, then I could take this right here and negate it to get -1, and negate it back again to get 1. So that would be a mark and unmark, just by setting it to -1, negating it, and then asking is it negative, that would be if it's marked or not. And then taking the absolute value would be unmarking it. Okay? So it's got to be a nice invertible function here. The problem is negating it on 0 doesn't tell us anything. It gives us the same input as the output, so you can't tell if node 0 is marked or not. I mean, I guess you could have another flag just special for node 0. Ugh, right? That would be ugly. Okay, so what I do is this. I mean, you could, if you had access to low-level bit arithmetic, you could actually set that 0 bit. So you could take, suppose you have an 8-bit number, you could just flip the last bit. That would work. But arithmetically, that's kind of a weird operation. That's not negation. That's like is that a ones complement? No, it's not even a ones complement. I don't know what it is. I could have used a ones complement as well. A ones complement would map 0 to all ones vector, which would be in 2's complement of -1. So a logical bit negation would take 0 and map it to -1 and vice versa, and 1 would map to 2 or -2, something like that. Okay. But I don't do that because there's something else I would like to do here with this marking idea. I use this marking notion elsewhere. Okay. It's also convenient to have a notion that, okay, here's a row index, and it's in the range 0 to n-1. Or here's a row index, a valid row index, but it's marked. Or here's nothing, a null. There is no such row. And what representation then do we want to use for that? So there's really 3 states. A valid row that's been marked, and nothing, an empty. It's going to be like a placeholder. I'll put something there, or it's something I'm not yet computed. I don't know the row index, or you're going to find that it'll be useful later on in the text, in the book, in the class, whatever. This if I do ones complement, I don't have such a convenient nothing number where 0 would be a nice nothing, but actually 0 is a valid row index. If I was writing this in Fortran, then 0 would be the perfect answer, but I'm not. I'm writing it in C. So I do the following: 0, 1, 2, 3, 4, and so forth. These are valid unmarked indices. They're valid and they're unmarked. -1 is, I define in the code, I call it the word empty. Nothing. It's like a null pointer, if you will. Okay, it's a nothingness. And so these negative numbers over here are going to be valid, but they're going to be marked indices, rows and columns, whatever. Okay. And so now here, of course, I'm marking column pointers, not row indices, but it's the same kind of effect. I mean, 0 and above are all valid. -1 denotes I haven't computed it yet, and then -2 and beyond are going to denote valid things, but are then marked. And so now what I want to do is if I have a mark on empty, I want it to give me empty, -1. So if I do something to empty, I want to get back the value empty. It's going to act like the 0 over here is, but I can't use 0 because that's a valid index. So 0 should go to -2, and -2 should go to 0 if I flip it again. And 1 should go to -3, and -3 will go back to 1. So it's a self-inverting function, just like those others are. But this is now the function I want to use, because now I can have a space of a positive greater than or equal to 0 valid thingies, indices or column pointers that are unmarked. I can have the same thing but with a marked state, and I can have a thing in the middle if I need it that says neither of the two. Okay. So the function that does this, that does the marking, is just negative, negative x minus 2. That's the function that does that. If you take negative x minus, if you have f of x computed as negative x minus 2, the inverse of this function is the function itself. And you get this. If you apply this to negative 1, you get f of negative 1 is negative 1. F of 0 is negative 2. F of negative 2 is 0, and so forth. That's the function. So it's a little odd. It's not a 1's complement. It's not a 2's complement. It's a symmetric complement about negative 1, or I don't know, what do you want to call it? I just made it up. That's why it's so ugly. It's like, ugh. Just hide it in a macro. I don't want to look at it all the time. It's ugly. Negative x minus 2. What is that? But there it is. It's flip. And so to mark something, I just say, okay, to mark the jth entry of a vector w, I just say wj equals flip of wj. So that does the flip. This is the CS flip is this function f over here. To unflip, this is akin to the absolute value. All right? I'm going to take the absolute value and remove a mark if it's there. And so I can ask if it's less than 0. It doesn't matter whether empty is marked or not. You can't tell, so it doesn't really matter. And so when I put a line here, I can say, well, if it's negative, then it's been marked. So the empty, if you will, is always marked. So that's what the Boolean test here. If wj is marked, it means it's just less than 0. So the empty token I consider to be always marked. And there's no way of unmarking it. So empty is marked in this scheme. So if you ever had a node negative 1, that node doesn't exist, but it's also marked, which is kind of handy actually, because if you have a graph that's partially constructed, and the nodes aren't out there yet, but you have an edge to a node that doesn't exist, you have an edge to a minus 1, oh, but that node's already marked, you've done, so that may or may not be what you want in any given algorithm, but it's a convenient thing to be able to assert that as you're reasoning about these functions. So anyway then, so I ask if it's not marked. Now, because I'm using a vector that starts out as all unvalid and unmarked here, the GP pointers. They're not row or column indices here, but I don't care. I'm using, these values are pointers into my data structure, but they're 0 and above. And so if I want to preserve the value 4, or the value 2, let's say, but I also want to be able to flag that position, then I can use the column pointers plus the marks at the same time, in the same memory, with this function. So is that clear? And so I ask, is the ith entry, and I is bi of p, this is the row index in column k, of this work vector, this vector here, is marked or not? And I'm actually tweaking the column pointers. If you look carefully at the use of my code, you will find that I do not do this actually to any input MATLAB data structure. I could, but I'm playing fast and loose with the rules of MATLAB. You're never supposed to modify the inputs to a MATLAB function. You can physically do it. You can actually do it, but it's a bad idea. And MATLAB has an assertion that, an assumption that if you pass a parameter to a MEX function as input, then it is not modified. It's not freed. Some of you freed your input, MATLAB inputs. You get, the seg faults will galore that way. MATLAB will assume, and the standard requires that your MEX function does not touch, it can read only the inputs to that MEX function. Can't modify them. So you could, if you apply this, it's like, ooh, you're starting to change the input. That's dicey. However, it's all going to be cleaned up when it's done. It's like, just close the door. Okay, we bash this data structure, this input matrix, and mangle it, and then, okay, the boss is coming back. Put it all back in order. Oh, here, we're fine. By the time we return, the matrix is back in order. So the caller can't tell. So it's sort of like driving 10 miles an hour faster than the speed limit. Right? If the police officer is not around, you won't be able to see it, but you really are breaking the rules there. It's just that when at the end of the day, nobody will care, or know, actually. So anyway, so then there's the call to the DFS. Now this is the recursive code here. At the node starting at node I, DFS starting at node, is node I marked? Okay, if it's not, do the DFS starting at that node I. Return back the value of top. The stack then is growing, and forget P inverse, and here's the top of the stack, and there's the stack xi. And I also pass in this xi plus n. This is additional workspace that is uninitialized. And I forget what I use it for. I'll have to look at the next slide. I use it for something important. I should know, but anyway, I'll find out on the next slide. In other words, xi on input is actually a vector of length 2n. I'm using half of it for the stack, and the other half below here for some other workspace. So it's a size 2n on input, this array. And top is being passed on input, but it's also changing. And then I have the entire graph G, which I'm only going to touch part of. Then when things are done, when the DFS from this node finishes, so this is going to be internally, it could have been written in recursively, but it's not. But it's going to do the entire DFS starting at this node I here, Bi of P. It finishes. When it finishes, then we'll go to the next node of B and so forth. At the very end then, I've got my stack, I've got my list of all these row indices that I've visited. And those are also precisely the nodes that are marked in the graph. So to unmark them, I go and do this. So I go from the top of the stack down to n minus 1. So the top now, at the end of the algorithm, will point here. It's always pointing to the first unused position in the stack. So I'm going to go back and traverse over these row indices and fix up the marking. Because if I don't, I destroy the input. It's not a good idea. Yeah?
Wouldn't CS flip freak out around max int?
Yes, it would. It would do all kinds of gross things around max int.
But there's no check for that.
No, there's no check for that. Yeah. There's an assumption or assertion higher up that your matrices are going to be, let's see, how does this work? I think actually in 2's complement, there's one extra negative integer than there is positive one, right? But if you notice how this is used, you're going from 2 to minus 4. Oh yeah, so max int, the largest max int, the positive, I worked this out once actually, and the most negative integer and the most positive integer, they have different effects, and I think some of them one of them maps to the other, or one of them has a cycle or something like that. There's something peculiar that happens at the largest and the smallest, biggest positive and the biggest negative integer. Something peculiar happens there, and I forget what it is. I think it actually works for max int. That one actually maps. Oh no, it can't. Can it? I think it maps it to itself. Yeah, I think it does. So suppose 4 is the largest. No, suppose 3 is the largest integer. Suppose we have a 4-bit number system. Okay, let's figure this out. That's kind of an interesting question. Then if 4 is then the most negative number is this one, right? Let's see, what is that? It's negative 4, isn't it? 2, 3, 4, 5, 6, 7, 8. We have 8 number. No, I'm missing. 0. Wait a minute. What am I
You got
missing?
an extra bit.
Yeah. That's 7. There we go. Okay, so I have an 3-bit number system. I have 8 numbers. And yes, this is what it looks like. -4, the most negative number, does get flipped and unflipped successfully. But then 3 will map to itself. So yes, the max integer has this little weird... If I flip the max int, you get max int. But I don't worry about that, and here's the reason. If I have an integer index of size if you think of it this way, if you create a graph, and actually I worry about this. I do worry, in not necessarily in this code, but in my real codes, I worry about these kind of integer overflow effects. The Sparse in the book does not worry about an integer overflow at all. Okay. But, well, there's one place it does. I take that back. So, but mostly it doesn't. But I do worry about integer overflow. It's a real problem, especially on 32-bit machines. With 4 gig of memory, you worry about an integer overflow because you can have problems that cause integer overflow, and yet you can store them. So here's the thing. Think of it this way. If you have a matrix with a row index of max int, okay, well, certainly if you have a let's go to a column. Suppose you have a column index of max int. What does that mean? That means you've got memory space of at least 4 or 8 times that, depending if it's a 32-bit or 64-bit machine. And you've already represented this object. But you can't represent that object of that size because the memory space would be too big. You'd have to have a memory malloc that would say, allocate integer space, bytes of 4 times or 8 times that. And when it does it, it computes the size and it would fail. And so in my memory wrappers, when I say allocate, space for n integers, I assume n is okay. But then I take n times the size of, and I ask, did that cause integer overflow? If it did, I say, I don't have the memory. And I don't even try to call malloc. Malloc itself should fail, but there's that product in there. Malloc doesn't take 2 arguments, it just takes 1, which is a bad idea, actually. But at that point, you would check for integer overflow. What that means is that you can get nowhere near max int on a real problem. So, same thing for when I create a matrix and I look at the number of rows. If the number of rows is anywhere near 4 times max int, I just say, I'm not even going to pretend to create it. Because any of my algorithms which want to allocate space of order proportional to the number of rows, I can't do it. So I'll never get close to this boundary, is the idea, either for row indices or for column pointers or column indices or anything, because I'll never create such a big problem, because I could never represent it. You'll run out of memory space. So that's why I don't worry about it. I think about it, but I don't, and I realize, okay, I can avoid that boundary effect. Yes?
I think that the maximum limit for the INT type on 64-bit system also like 4 bytes. So the same as the 32-bit system.
For an int?
Yeah.
Yes, but we're not using ints any longer. We're using we're using pointer difftees now for these integers. The question was the ints. Well, it really depends. An int is compiler dependent. It's operating system dependent. And the same thing with a long and so forth. Whether you're in Microsoft land, La La Land, or whether or not you're in real space. But whatever it is we're doing here, I make the assumption typically that in here now with Sparse version 3 in particular, where the integer is a type CSI, that's a pointer difftee. So it's the size of a pointer, which means it's the natural size of the integer on your machine. If it's a 32-bit machine, it's 32 bits. If it's a 64-bit machine, it's 64 bits. And there's no way you can cause integer overflow with 64 bits because on any given machine because the memory space on a 64-bit machine, the virtual memory space, is not 64 bits. It's like 48 or something like that, right? It's typical 64-bit machines don't even exploit the entire 64-bit virtual memory space range. There's no way you can get anywhere close to this maximum number then. These things seem very esoteric, don't they? Extremely esoteric. But you know what? Until you hit them and your code crashes. And the MathWorks calls you up and says, hey, Tim, there's a bug. You don't want that to happen. So you hammer your code until these kinds of esoteric things just don't cause your code to fail. You worry about this stuff. I do. I know, maybe I'm obsessive. I don't know. I guess I must be. We're several minutes over, but we started several minutes late, so the tape is still 50 minutes long exactly. So let's finish here, and I'll pick up. I guess we didn't finish chapter 3, but with some good questions. But so we'll pick up from chapter 3 next Wednesday.